In cryptography, the Elgamal encryption system is an asymmetric key encryption algorithm for public key cryptography which is based on the Diffie-Hellman key exchange. It was described by Taher Elgamal in 1985. Elgamal encryption is used in the free GNU Privacy Guard software, recent versions of PGP, and other cryptosystems. The digital signature algorithm is a variant of the Elgamal signature scheme, which should not be confused with Elgamal encryption. Elgamal encryption can be defined over any cyclic group. Its security depends upon the difficulty of a certain problem and related to computing discrete logarithms. The algorithm, Elgamal encryption, consists of three components: the key generator, the encryption algorithm, and the decryption algorithm. Key generation: the key generator works as follows. Alice generates an efficient description of a cyclic group of order with generator. See below for a discussion on the required properties of this group. Alice chooses a random from. Alice computes. Alice publishes, along with a description of, as her public key. Alice retains as her private key which must be kept secret. Encryption: the encryption algorithm works as follows. To encrypt a message to Alice under her public key, Bob chooses a random from, then calculates. Bob calculates the shared secret. Bob converts his secret message into an element of. Bob calculates. Bob sends the ciphertext to Alice. Note that one can easily find if one knows. Therefore, a new is generated for every message to improve security. For this reason, is also called an ephemeral key. Decryption: the decryption algorithm works as follows. To decrypt a ciphertext with her private key, Alice calculates the shared secret, and then computes which he then converts back into the plaintext message, whereas the inverse of in the group, the decryption algorithm produces the intended message, since. Practical use: the Elgamal cryptosystem is usually used in a hybrid cryptosystem. That is, the message itself is encrypted using a symmetric cryptosystem and Elgamal is then used to encrypt the key used for the symmetric cryptosystem. This is because asymmetric cryptosystems like Elgamal are usually slower than symmetric ones for the same level of security, so it is faster to encrypt the symmetric key with Elgamal and the message with a symmetric cipher. Security: the security of the Elgamal scheme depends on the properties of the underlying group as well as any padding scheme used on the messages. If the computational Diffie-Hellman assumption holds in the underlying cyclic group, then the encryption function is one-way. If the decisional Diffie-Hellman assumption holds in, then Elgamal achieves semantic security. Semantic security is not implied by the computational Diffie-Hellman assumption alone. See decisional Diffie-Hellman assumption for a discussion of groups where the assumption is believed to hold. Elgamal encryption is unconditionally malleable, and therefore is not secure under chosen ciphertext attack. For example, given an encryption of some message, one can easily construct a valid encryption of the message. To achieve chosen ciphertext security, the scheme must be further modified, or an appropriate padding scheme must be used. Depending on the modification, the DDH assumption may or may not be necessary. Other schemes related to Elgamal which achieve security against chosen ciphertext attacks have also been proposed. The Kramer-Shoup cryptosystem is secure under chosen ciphertext attack assuming DDH holds for. Its proof does not use the random oracle model. Another proposed scheme is DHAS, whose proof requires an assumption that is weaker than the DDH assumption. Efficiency: Elgamal encryption is probabilistic, meaning that a single plaintext can be encrypted to many possible ciphertexts, with the consequence that a general Elgamal encryption produces a 2-1 expansion in size from plaintext to ciphertext. Encryption under Elgamal requires 2 exponentiations. However, these exponentiations are independent of the message and can be computed ahead of time if need be. Decryption only requires 1 exponentiation. Decryption: the division by can be avoided by using an alternative method for decryption. To decrypt a ciphertext with Alice's private key, Alice calculates. Is the inverse of. This is a consequence of Lagrange's theorem, because where is the identity element of? Alice then computes, which he then converts back into the plaintext message. The decryption algorithm produces the intended message, since. See also, Elgamal signature scheme, homomorphic encryption, references, Taher Elgamal. A public key cryptosystem and a signature scheme based on discrete logarithms. IEEE Transactions on Information Theory 31, 469 Euro 472 doi, 10.1109/tit. 1985.10570774a, AB Cryptutor, Elgamal Encryption Scheme, AB M. Abdullah, M. Bella, P. Rogaway, DHAES, an encryption scheme based on the Diffie Hellman problem, Elgamal, Taher. Advances in Cryptology, Proceedings of Crypto 84 inches. Lecture Notes in Computer Science 196. Santa Barbara, California, United States, Springer Verlag PPA 10 Euro 18 doi, 10.1007/3-540-39568-7 A.J. Meanses, P.C. Van Washot, and S.A. Vanstone. Chapter 8.4 Elgamal Public Key Encryption. Handbook of Applied Cryptography. CRC Press. Dan Binney. The Decision Diffie Hellman Problem. Lecture Notes in Computer Science 1423, 48 Euro 63 doi, 10.1007/BFB00548551A.